Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
With that, I don't know what to introduce you because you all seem to know him already, but I'll do that anyways for the people who may be watching. So it's a great pleasure to have you here, Dave. Dave Malls got his bachelor's and master's from MIT. Then he got his PhD from CMU in 2001. He's quite an entrepreneur. While he was finishing up his PhD, he was picked up by this company called FreeSpace and became one of the founding members of that company, which was about metropolitan area wireless networks. And then he went on to start his own company on network management software. And then he decided that he wanted to get back into research, came back to CMU for a postdoc, and was instrumental in getting something to the order of like $7.5 million from NSF for this 100 by 100 project. It was very exciting. And he's right back into research as if nothing has changed. So it's a great pleasure to have him here, and take it away.
Thanks. Hi. I'm sorry I'm getting over a cold, so if I cough a couple of times, there may be some hiccups in the audio. I'm here to talk with you about one part of the 100 by 100 project. So the 100 by 100 project in large is thinking about what would it take to be able to build a network that could deliver 100 megabits of connectivity between all 100 million American homes. Part of the problem to be solved there is how are you going to manage such a network? And I won't say the work I'm going to talk with you about today is, the answer, but we think it's along a trajectory to that answer, and it certainly solves a lot of problems with network management as they exist today. Basically, this is joint work with colleagues all over the place. Albert Greenberg from AT&T Labs Research, Gisli Amundsen from Reykjavik University, Jennifer Rexford, now at Princeton, Jeffrey Shea, now at Naval Postgraduate School, and colleagues from Carnegie Mellon. So I'd like to start with the frustration I'm sure we have all experienced. You're sitting at home and you want to get some data off your computer at work. Maybe you want to SSH into it. Maybe you want to get some web data off of it, and you can't. It's not that it's just a little bit slow or something. Nothing seems to be getting through. You try everything you can. You reboot all the monitors, yada, yada, yada. Nothing works. And then at some point in time, minutes or hours later, it starts working again. And you can't predict why. You have no ability to predict when it's going to happen again, so you have no ability to plan your schedule. You don't know whether you need to go into work this morning, or can you telecommute for a couple of hours. And unfortunately, network operators are not much better at predicting outages of this kind than you are. And that's a big problem for building robust networks. So in this talk, what I'm going to do is I'm going to explain to you a little bit about where some of these really hard to find outages come from, and then two different approaches that we might take for trying to make that better. So first I'm going to have to tell you what today's networks look like, something about the mechanisms that go into them. Then I'll talk about some work for predicting network behavior. And finally, I'm going to summarize and say, really, this is actually really hard. Maybe we can redefine the problem with a new architecture and make it easier. So when I say network, I have to first start by explaining what I mean. The first thing I have to say is the internet does not exist. There is no such thing as the internet. It is made up of a bunch of separate networks which are all interconnected, hence the internet. So what are the networks that make up the internet? Well, they vary in size. Generally, the networks that comprise the internet have between 10 and 1,000 routers each. Just for sort of managerial reasons, it seems to be that's the way the cookie is cut. Now, what defines each of these networks is often an owner. There's some organization, a company, a government organization, or whatnot, that defines the network. This network was built to serve the goals of that organization. Now, there's also a lot of topologies that you'll find with networks, meshes, trees, rings, so on and so forth. So when I talk about networks, what you should be thinking in your mind are things like the following. Imagine the network that connects the computers on Microsoft's campus. That's a good example of an enterprise network. There's also access networks, everything that connects up DSL and cable modems, backhauling all that data from people's homes to a collection point where then it can be connected to other networks. Metropolitan area networks. These are networks that generally built in rings that connect up all the businesses in a large city. Inside a single company, for example, in the MSN data center, there are data center networks local to that data center. Their boundary is sort of inside there, and then they connect to networks on the outside. Finally, you could think of sort of transit backbone networks, things like the networks run by Sprint and AT&T. They've received a huge amount of the focus, but as you can see, they're only one example of the many different types of networks out there. So I hate to say it, but this is a conventional view of a network in many people's minds. This is actually what we teach in undergraduate classes. I actually stole this off a slide that I have used to teach undergraduate classes, I'm afraid. And in this conventional view, we say, a network is a collection of boxes and links, and that if you want to know how packets get from router G to router H, you take the physical topology here, and you run Dijkstra's shortest path algorithm or something on it, and that tells you which way the packets are going to go. Unfortunately, this is almost entirely wrong. Knowing how routers are connected, knowing the physical topology, tells you almost nothing about the ability of two hosts connected to the network to communicate. And that's the key thing to understand when we're trying to understand the causes of network outage, which is basically two computers that should be able to communicate and can't for some reason. Let me quickly go through sort of some background. This is what network gear actually looks like. When we talk about routers or boxes, this is an example of a Juniper T640 router, and stacked on top of it a little bitty Juniper M5 router. This picture is taken from Abilene. This is the Atlanta POP Internet 2, which is a national academic backbone network. So when we talk about routers, you could think about things like this. These are what direct the flow of data, the flow of packets through a network. And these boxes are connected together with this spaghetti of cables and wires. Some of them stay inside of this machine room. Some of them go out across the country. Now, networking people are known for using acronym soup and huge amounts of terminology. However, when we're trying to think about controlling and managing networks, we can actually use a pretty high level of abstraction. And in fact, we want that high level of abstraction. So when we think about the boxes in the previous picture, really those are routers or switches. But the difference between a router and a switch is really insignificant. It's basically a marketing term. It's the only difference between those. And in terms of the links between boxes, there are many, many different types of links. There's Ethernet, like what connects up your computers in your office. There's SONET, often used in metropolitan area networks. There's things called T1s. But the differences among these are actually not really important when we're trying to understand why networks work or why they fail. Because showing you pictures of actual routers rapidly becomes unwieldy, I'll need sort of a graphic iconography. So when I want to talk about a router or switch, I'll use a blue circle like this. And when I want to talk about a link, I'll use a thick black line like that. Now, links are connected to routers at interfaces. An interface here means a hunk of hardware. It's a port that you actually snap the cable into. It is not a software interface. Hosts and servers are actually just other boxes connected to routers via other links. Oh, and I sort of have some gray routers and links at the edge of the slide to indicate that this is just one small part of the network we're looking at. Think about the network sort of going off on both sides of the screen. For the purposes of this talk, networks are going to traffic in packets. All right? There are circuit switch networks. But for here, information as it goes across the network is broken up into these packets. A packet is a sequence of bytes. At the head of each packet is metadata, basically a number saying where the packet came from, a number saying where the packet's going to go to, and some other information. My guess is people here are pretty comfortable with this. Now, let's talk about the data plane of a network. So at the physical layer, we have routers connected by links. And this sort of begs the question of, if you have a router with two interfaces and a packet that comes from a host or server, which interface does the packet go out? Well, the answer is given by what's called a forwarding information base, more commonly known as a forwarding table, which is a data structure in this router that it consults for every packet it gets, matching some of the fields in the metadata against the table. So a packet going to destination A for this router is going to go out the left interface because that's what the forwarding table tells it what to do. Now, data plane also consists of things called packet filters. So let's say I have two packets both going into this router, both destined to destination B. The forwarding table says packets to destination B should go out this interface. However, just because two packets go in doesn't mean the two packets are going to come out, because I can specify packet filtering rules on a particular interface that say, test some other fields in the metadata. A packet going from source address A to destination B should be allowed onto this link. But if you see packets going from source address C to destination B, drop them. Sort of the big difference between packet filters and fibs is that packet filters generally have higher granularity. You can test more fields in the metadata. Now, there are many other sort of mechanisms that exist in the data planes, things like queuing disciplines, packet transformations. Maybe the case that when a packet goes in, the router actually writes it and a packet comes out. The ideas I'll talk about in this talk are sort of applicable to these things as well, but I'm going to focus mainly on forwarding tables and packet filters just for this discussion. Thank you.
So are packet filters confined to the edge of the network, like access routers, or are they actually used everywhere?
So as a result, we're going to see in a few slides, they're actually everywhere. So hang on to that question. I'll get there. The next thing we have to talk about is what's called the control plane of a network. Basically, where do the entries in this forwarding table come from? Where do the routes in the forwarding table come from? Well, it turns out that there's this very large distributed system, which is generally known as the control plane, whose job it is to populate these tables with routes. And unfortunately, it is failures of this large distributed system that are largely responsible for network outages that are really hard to debug and persist for long periods of time. So to understand what the network's going to do, we have to look into the details of how this distributed system functions. Here's how we're going to start thinking about this problem. So on each router, I have a routing process that runs, and it's the job of that routing process to push entries, routes, into the forwarding table. So each of the routers in the network is generally going to run a routing process, and they're going to exchange information with what are called adjacent routing processes, basically processes they've been configured to exchange information with. Now, the format that that information takes is going to vary depending on what routing protocol each of these processes is using. And as I said, networking people are known for their acronym SOUPs. Here are the names of a bunch of different routing protocols. But when we're trying to understand the control and management of networks, the difference between these protocols is not particularly important. They affect basically the format of this information. So one routing process may say, hi, I know how to get to A and B. And another routing process may say, hi, I know how to get to C and D. Now, the other function of routing processes, or routing protocols, is they provide the logic for breaking ties. So if two routers both advertise routes to the same destination D, it's up to the particular rules of that routing protocol to decide which one of them is going to win. And should the forwarding table for this router say packets to destination D go left or right? In this case, the rules decided that they should go to the left. Now, why was this done, routing information being distributed between routing processes? Well, it's for resiliency. Let's say I have a very simple network. 3 routers connected together with links, routing processes on each router, all adjacent with their neighbors, and some host or server D connected to this router here. Well, this router is going to generate a route to D because it's directly connected to it. It knows how to reach D. That routing information is going to flood along this routing process graph, so that if one link were to break, it may be the case that D is no longer reachable along this path. However, the routing information on how to reach D will flood along the redundant path in this graph. And so this routing process will know, D is still reachable, and it'll have the information that it needs to know to update which interface it sends its data out. This begs the question. It seems really simple. How complicated is this in real networks? I would argue that pretty much nobody had a good sense of this until we actually went out and did an experimental study to look at this question. Well, some of these results were reported in SIGCOMM last year. Basically, unfortunately, there are no documents, or very few documents, that describe the architecture of this distributed system that is the control plane of a network. Why? Well, 1, the people who do these are very bad at documenting. 2, networks are continually evolving. Even if there was an architecture document when the network was first rolled out, the next day, somebody probably made a change to the network, and that wasn't updated in the documentation. So how do we look or understand what this architecture is? We use reverse engineering. Basically, what we start is what are called configuration files. The programs that are loaded onto each of these routers that configure the distribution of information, basically configure that distributed system and set it up. And we analyze them to see what this distributed system looks like. We applied this technique to 6 Tier 1 and Tier 2 internet backbone networks, so big transit networks, and then 25 enterprise networks. The size of these networks varied from 10 to 1,200 routers, and interestingly, 4 of the enterprise networks were significantly larger than any of the backbone networks, and they were also more complex. There seems to be this myth that backbone networks are the really interesting complex beasts. It's actually not true. Enterprise networks are often way more complicated. This is a picture of a router configuration file. I don't expect you to read the whole thing. I want you to appreciate how much pain and suffering we had to go through. The things to take away from this is that it's very low level. It's assembly language. There are no variables. There are no procedures. There's no abstraction. What you have here is a huge amount of mechanism, all with individual IP addresses and numerical identifiers that associate themselves with other bits of things. There's configuration for individual routers. There's configuration for routing processes. And there's lots of policy. And I'll come back to that policy in a second. And for each network, there's actually quite a lot of this configuration commands. So this is a distribution of the size of the configuration files for 881 network with 881 routers. So you see some of the configuration files are very large. Some of them are, well, only have a couple hundred lines in them. But the network overall has well over 300,000 lines of configuration. A human being couldn't understand what's going on in this network by just trying to read the configuration files.
Does this include comment lines? Or
We actually stripped comment lines. And it turns out these configuration files had to be anonymized before I could get access to them. And part of that involved stripping out all of the comments. So,
do you have a sense for how many of those configuration lines are different? Like there are going to be chunks of that configuration that are going to be the same. You know, things that define what you do with peer routes, what you do with customer routes, and.
It's a good question. I'll take that one quickly here, although it's going to require scanning down. Let's see. I think it's in here. I will show you a slide with sort of the differences among those later, if you'd like. It's actually not in this backup set. OK. So we did this sort of analysis. We pulled out the architecture of this distributed system from all these networks and started looking at it. What are things that we saw? Well, the first thing we saw is that routing processes are used not only to distribute routing information, but also to implement policy. So for example, as routing information moves through the network, routers might filter it. So while reachability to A and B may go into a routing process, it might only announce reachability to destination A out to its adjacency. Now, why might that be? Well, sometimes it's security policy. Basically, the policy of this network might be that hosts over in this part of the network are not supposed to be able to send packets to destination B. So by filtering the routes to B, the network designers implement that security policy. It might also be the case that they're trying to implement some kind of resource policy. Maybe this link is actually very expensive, or they want it to be lightly utilized for some reason, so that destinations over here can use this link to talk to destination A. But if the hosts over here want to talk to destination B, they're going to have to find some other route through some other way through the network. Now, we did see that packet filters were used extensively sort of throughout these networks. There's sort of this myth, or the assumption was that the packet filters would be found mostly at the edges of a network to sort of set up some kind of security perimeter. Instead, we found them throughout. This is a CDF, cumulative distribution function, against where packet filters are found inside the networks. And what it shows is that in 30% of the networks, none of the packet filters were on interior links, sort of meeting the expectations. However, in another 30% of the networks, more than 50% of the packet filters were actually applied to internal links of the network. So they really were found sort of throughout. What were those packet filters doing? To some extent, they were protecting routers from attack. That was one common thing that we saw. But a more common thing even was implementing what we call a reachability matrix. I'll talk about this more later. But effectively, trying to define which hosts and which applications can communicate across the network. The other thing we saw them being used for extensively was localizing traffic. For example, keeping multicast in one portion of the network, keeping it from spreading. We also saw lots of mechanisms for action at a distance. Let me show you how this works. One router might create a route to destination A, and it sticks a tag on it, basically an annotation on the routing information. And as the route flows across the routing process graph, the tag goes with it. And some other router, someplace else in the network, is going to test that tag, and based on it, decide what to do with the route. So the tagging logic might say, if the route has tag 12 on it, then it can go out the upper interface, and it shouldn't go out the lower interface. Well, I call this mechanism for action at a distance because it does, in fact, look like magic when you see this happening in real networks. And you can also see lots of potential problems. For example, there's nothing magical about the number 12 except as it's a global constant that exists in the mind of the network designer. If someone else tags a route someplace else with constant 12, this router is going to act on it just the same. Right? So there's a potential to set up little time bombs for yourself where someone doing something that looks locally reasonable can cause an unexpected effect in some other portion of the network.
Just a side question. How did you access all this information from the routers? Did you actually ping it? Was it in a central database?
So in this case, all of this analysis was done by looking at these configuration files. So effectively what I have is I have the programs for the routers that tell me which routing process runs on each of the routers, which routing processes are adjacent to each other, and all the policy that gets applied. So I actually am not, a strength and a weakness of this approach is that I don't need the running network. All I need is a description of the programs running on the network, or that set up the network.
And these are sitting where?
So these are router configuration files. In a real network, when you bring up a router, you load this configuration file program onto it. And that then tells it which of the other routers in the network it should start communicating with. I gained access to these primarily through a partnership with AT&T. And as I say, I can talk more about the data preparation and the details of that offline. But AT&T has both their own networks and also does outsource management for a number of enterprises. One other thing that we saw very quickly is that there are actually multiple routing processes running on each router. This is one router running an OSPF process, a BGP process, and another OSPF process. So OSPF and BGP are names of routing protocols, but really think about them here as sort of processes on a modern operating system. They each have some store of routing information that they know, that they've learned from talking to other routing processes, but they can't share information with each other unless there's policy explicitly configured to move routing information back and forth. Now, why is this important? Well, if I have a client connected to one router and a server connected to the other, determining if the client can talk to the server requires seeing whether the route to the server, which starts off in this router, can actually make it through this routing process graph, basically making it through all these policies, eventually getting to the router that the client's connected to. If the route is filtered at any point, the client won't be able to talk to the server, even though a physical connection exists between them. Okay? And it's actually really complicated in real networks. So this is a picture of what we call the routing instance graph of that 881 router network. You will note that there are not 881 circles on here. What I've actually done is taken the network to another level of abstraction. Basically, all the routing processes that have roughly the same routing information in them, I've collapsed those into a single circle. And you can see that there's still, this is a pretty complicated graph. Determining whether a host connected to one of these routing processes can talk to a host connected to another routing process requires figuring if routing information can actually make it all the way across this graph. So a routing instance is basically this notion, it's an abstraction of this graph. Basically, if I have a number of routing processes that all have effectively the same routing information in them, more or less a policy-free zone, then I'm collapsing them together into a single routing instance. So then an edge between two nodes is a point where routing policy is applied, such that the routes in one routing instance may be different than the routes in another routing instance because some of those routes have been filtered.
So let's look at one of the OSPF green blocks up there. Mm-hmm. Would you collapse that with the second OSPF block down there or not?
In this case, if there's no policy applied to any of these adjacencies, then yes, we'd collapse them. Does it make sense?
I think the question was related to how this middle node, or maybe this is just my question.
Sure.
The middle node seems to split to two different nodes in the routing instance graph.
Yes. So in this case, a routing instance picture for this this slide would actually show three routing instances. Say, one of them for these green routing processes, one for this red one, and then one for these blue routing processes. So long as the only policy is actually being applied here. Generally, it's the case that policy is applied sort of inside of a single router. It can be applied across adjacencies, but.
So what exactly is your definition of policy? What is a policy and what is not a policy?
So a policy is basically anything that's going to filter routes out or change routes. So like that tagging notion, that would be policy. The thing that applies a tag, or the thing that's going to test on a tag. That's an example of policy. Other examples of policy would be things that say any routes that match this subnet should be thrown away, or only routes this match this subnet should be permitted. That's policy. Make sense? Okay, make it?
I'm a bit confused. So, I mean, in general, a node may not apply any filters or anything. It might just propagate information, but it still sort of, let's say I hear multiple routes to destination.
Yes.
Okay. I'm going to pick the best one.
That's right.
One of those based on some criteria.
That's right.
Would that be considered as applying policy now?
No. So in that case, that's not an application. That's basically this. So each of these routers, take this router here. It's running 3 routing processes. It needs to populate its forwarding table. It's going to do that by somehow selecting the best routes out of all of these routing processes to put them in this forwarding table. But I'm not including the forwarding tables in this routing process graph, basically because it's a sink in the graph.
But I guess my question is, I mean, this guy hears multiple routes and then picks the one that's best for him.
That's right.
Based on something. So the one he picks, the route he picks to the destination could be different from the one he heard from one of his neighbors. But are you going to collapse these two nodes together, or are you going to keep them separate?
So in this study, I will collapse those two so long as it's the same destination.
Even if the routes they actually...
Even if the routes they pick are different, because they have reachability to the same destination. It's sort of a, if you let me continue, I'll show you how I'm going to use this kind of graph.
You're just trying to figure out problems with policy and not routing loops and other things that other...
That's right.
So I think that's the key here. He's just trying to figure out issues with the policy.
Right. Routing loops are generally transient. I mean, under proper configuration, given some BGP.
Problem is the more important thing.
It's somebody else's problem.
And so let me see if I can characterize what you're trying to do. You draw an edge on your graph where, if you look at the total space of routing policies, there's sort of three interesting ones. There's 0. I won't send it because I don't have a physical link, or I just decide I'm not going to. There's 1. I'll always send it. I don't have anything. And then there's something in between.
Right.
Your edges on your graph correspond to that third case. And
well, okay. So policy edges correspond to the third case.
That's what edges on your.
That's right. Edges on this abstraction.
On that graph.
Yes. Edges on this abstraction correspond to the third case.
Right. Okay. I got it.
More questions? Okay. I'm gonna.
So can you explain why there's a segment of 3 nodes that are not connected to the rest?
I would rather not focus on this one thing because I can go into the details of each one of these networks for hours. Let me give you a high-level view of the problem and ways of approaching it. So takeaway points that I'd like you to, from sort of this very quick study of a bunch of networks. So first off, networks deal with both creating connectivity and preventing it. I mean, a lot of people think, oh, the job of a network is to connect all the hosts. Not true. It's supposed to prevent connectivity between certain sets of hosts. Networks are controlled by these complex distributed systems. You want to understand what the network's going to do, you got to understand this distributed system somehow. You can't focus on individual protocols. There's been a lot of focus on BGP. There's only one protocol. It's actually only a few dots in sort of that very complicated graph I showed you. If you want to understand what the network overall is going to do, even a single enterprise network, you need to understand the composition of multiple protocols. And to sort of advance this, we came up with a bunch of abstractions that I have glossed over. Okay. Now let's look at a way of sort of trying to predict network behavior. Okay. I'm going to start with a very simple question, one so simple that I think we often don't think about it, which is reachability. If host A and host B are connected to a network, and A sends a packet to B, does the packet get through or not? Can the packet get through or not? Clearly, this is going to depend upon how the routing protocols here are set up and configured, the state of the forwarding tables, what packet filters happen to be in there. However, predicting reachability is the key thing you need to do if you want to understand network survivability or security. What do I mean by that? Well, survivability is basically our notion of there are some packets that we want the network to always permit through. The network should never actively try and stop those packets from getting through. There's also a set of packets for security reasons, we want the network to always prohibit from getting through. For example, in the case of a virtual private network, there may be sets of hosts that are supposed to be isolated from each other. And we want some ability to evaluate the survivability and security of a network. Let me make this more concrete with an example. Let's say I have an enterprise network that has 2 locations, one in Chicago, one in New York. And in each location, there's a data center and a front office. Okay? Let's assume we have a very simple routing design. Each one of these routers is going to run a routing process, and they're going to exchange routing information out, all of the links connected to them. Now, let's say it is the policy of this network that they want to implement this reachability matrix. Basically, they want it to be the case that computers in the front office can communicate with servers in the data center of that same location. But the front office computers should not be able to communicate with data center servers of the other location. Now, it might seem weird, but that's actually pretty common in networks like insurance business, where sort of one mother company owns both the data centers and the network, but the agents in each office are effectively competing with each other. Now, let's say it's also the policy of this company that the computers in the 2 front offices should be able to communicate with each other so they can do chat or what other kinds of applications. But they don't want agents here to be able to screw up or send SQL queries to the servers in the data center of the other location. The most common way of implementing such security policies today is to use packet filters. For example, the network designer might put a packet filter on this interface that says, if you see a packet coming from the New York City front office down here, well, then drop it, because that shouldn't be allowed into the Chicago data center. Similarly, if you see a packet coming from the Chicago front office here, drop it, because that packet shouldn't be allowed into the New York City data center. And it turns out that this network design actually implements the desired reachability matrix. Until one day, when the people who run the data center decide that they want to start backing up data between their two locations. And so they put in a new link. Now, because these packet filters exist, you might think, well, the data center is successfully cut off from the front offices. We're fine. But we're actually not. Because this is now another alternate route to reach into the data center. So if the Chicago front office sends a packet to the New York City data center, it'll be routed this way, where it's allowed through this router, because it's from the Chicago front office, across the new shortcut link, and into the New York City data center.
The packet filter is associated with the interface.
That's right, because it's associated with the interface. Now, the most common way to fix this, just the way you fix buggy code, of course, is if it doesn't work, you add more code until it works. And so usually what they would do is they'd add another packet filter to this interface and this interface, saying, OK, now if you see a packet coming from the Chicago front office here, drop it. So now the packet, the wayward packet, will get dropped at that interface. But notice what we've done. It is the case that we want packets to be able to get between the two front offices. Now, if this link were to fail, there is still a physically connected path. However, packets can't use it, because they're going to get thrown away by that packet filter right there, even though they're effectively harmless. So the state of the art in reachability analysis is basically experimental in nature today. You build the network, you connect the hosts, and you try and send packets to see if they get through or not. So ping, traceroute, there are fancy monitoring tools that exist. But they all have the property that they only check the paths that are currently selected by the routing protocols. There's no ability to do sort of what-if analysis. I'd argue that what we want is the ability to do static reachability analysis. It means we have to be able to predict reachability over multiple scenarios from nothing more than a description of the network, so that we can find these problems before we actually change the configuration of the network and create them in the real world.
This whole thing seems to be a case of Cisco doing stuff that should really be done end-to-end, right? I mean, if you do flooding attacks, which I guess could be a concern,
yeah.
The rest of the stuff can be accomplished by just doing checks.
So,
Right?
so you're proposing, why don't we just use the end-to-end argument to the extreme and use something like IPsec on all of the end hosts to fix all these problems?
No.
Well, OK, maybe it's not IPsec, but some kind of end-to-end mechanism.
Yes.
The fact of the matter is that people are willing to pay network providers to implement this kind of functionality. There are other ways to achieve it, but I'm telling you how it is today. And basically the reason is, I either have more complexity in maintaining my end systems, or I sort of solve the problem once in the network. It's been very appealing to try and solve the problem in the network, or at least reduce the impact of misconfigured end systems by having backstop measures in the network. How can we predict reachability? First thing I need to do is introduce a little formalism, because we're going to end up creating an algebra. I'm going to define what we call the instantaneous reachability, R sub ij of s, to be the set of packets that the network will allow from router I to router j when it's in forwarding state S. What do I mean by forwarding state S? Imagine taking a snapshot of the contents of all the forwarding tables in the routers in that network. That's what I mean by forwarding state. We call this the instantaneous reachability, because as routing protocols reconverge or whatnot, or advertisements change, links go up and down, the forwarding state will change over time. And the instantaneous reachability will then also change to reflect that. How could we calculate the instantaneous reachability? Well, let's say I had some helper variable, f sub ij of s. And what this is going to do, this f variable, is it'll tell me what packets can get from two routers, R2, say, to R1, when we're in forwarding state S, over just this one link. If I had this helper variable f, then computing the reachability between any two routers I and j becomes a question of finding the packets allowed along any paths between I and j. So I can find the paths between what packets can get from, say, R3 to R2 to R1 by taking the intersection of the packets that are allowed through this helper variable f and that helper variable f. That's what this part of the equation more or less says. The packets that can be allowed along a particular path is the intersection of all the f helper variables along that path. Then to find the instantaneous reachability from I to j, I just take the union over all the potential paths because, the packets would have to take one of them, or they could take any of them potentially. Now, that might seem big and hairy, but it turns out you can use a dynamic program to calculate it, and the complexity bound is not bad. Yeah.
So it seems by unioning over all the paths, you're also going to union over all paths that allow it that you can you're going to get forced to forward along one path, one direction, and then it'll get dropped.
Aha. So that's right. So these f's are going to be critically important. So basically, some of these f's may actually subtract out packets, right? So it may be the case that a particular ping packets aren't allowed along this path, but they might be allowed along this path, right? And so the f variables along here will basically not include any ping packets, and the f variables along this path will include ping packets. Okay? The reachability overall.
Well, I'm just concerned that you may be allowed to go. It may be that the path you have to take is from R3 to R4 to R1.
Yes.
But it could be that the routing table at R3 forces the packet to go to R2, where it subsequently gets dropped.
So you're asking yourself exactly the right question. So where do we get these Fij of s's from?
Oh,
and the real problem is that there are two very different beasts at operation here. There's routing protocols, which are dynamically exchanging information in real time, changing the contents of the forwarding tables. And there are packet filters.
Okay.
How do we get these down into sort of the same substrate, the same currency, where we can jointly reason about both of them? And the insight is we're going to treat routes as dynamic packet filters. Let me explain what I mean. Let's say we knew the forwarding state at R2. So we know exactly what routes are in its forwarding table. Destination A goes to R3. Destination B goes to R1. What I can do then is sort of pretend that there are extra terms in the packet filters on these interfaces that'll say only packets going to destination A or destination C are allowed out this link. Only packets going to destination B are allowed out that link, because any packet not matching those destinations would be dropped by the router because there's no route to forward it. And this router with this forwarding table would never send packets to destination C out that link.
What do you do about multicast?
Multicast, I would have to actually put it on both ones. That's a good question. I haven't really thought about multicast here. That's a very good point.
Describe that. Your formalism should describe it.
I think it'll do it, but I actually haven't thought that one through. So
you have to keep the notion that it's the same packet on both interfaces.
Right.
His formalism is in terms of sets. It should work fine.
Well, let me show you. So that's a good point. Maybe we should talk about that offline. Let me show you what I'm going to do with this first, and then you'll see whether you actually think it's worthwhile or not. So I'm going to claim now that we still need to know the exact forwarding state S, right? But it's impractical to know S exactly for a whole bunch of reasons. But I'll also argue that knowing the instantaneous reachability, the reachability for a particular forwarding state S, is effectively useless because it's only applicable when the network is in that forwarding state and the network is going to move along multiple forwarding states. What we'd really like to be able to do is predict the behavior of the network over a set of forwarding states. And it turns out that predicting the behavior over the set of all possible forwarding states is much, much easier than predicting the forwarding state in any particular one state. Okay? What we're going to do basically is define bounds on the reachability. So we're going to define the lower bound on reachability to say, let's take the intersection over all possible forwarding states of the instantaneous reachability. If we can compute that, then the set of packets here are the set of packets that are permitted between I and j in all possible forwarding states. Okay? So that's good if you want to know the survivability of your network, because basically packets in this set are never prohibited by the network from getting to I to j. Similarly, we can define an upper bound on reachability to be the set of packets that are allowed between I and j in any of the possible forwarding states. Okay? So this is the upper bound is then the set of packets that could potentially get between I and j. That set itself is not particularly useful, but the inverse is. The inverse is the set of packets that are never permitted, or always prohibited by the network in getting from I to j. And that's what I need to know if I want to validate a security policy. Okay? And we can talk more about sort of how you're going to calculate these kinds of things. But let me sort of show you an example of how this can be useful for a particular example. let's say before I add the shortcut link, I take our algebra and I just crank it. It's a mechanical rote process. What I'll end up doing is computing that the upper bound on reachability between the Chicago front office and the New York City data center includes the set of packets whose packet source is New York City front office. What that is saying is that if you could give this router here a packet with a source address of New York City front office, that packet, under some situations, could make it to the New York City data center. Effectively, if you spoofed addresses here, you could talk to the New York City data center. Is that a major problem? I don't know. That's up to the network designer. But this technique caught it, and maybe it wasn't obvious beforehand. Another nice thing about this, though, is that if you add this new link and then crank the algebra again, you'll find that now the upper bound of reachability definitely includes packets whose source address is the Chicago front office. So now the algebra is telling us that if the Chicago front office just legitimately sends a packet to the New York City data center, there are some sets of forwarding states under which that packet could actually get to the New York City data center.
So, correct me if I'm wrong, but doesn't it look like your algebra includes any notion of link weights? Is that correct?
That's correct. It doesn't.
Okay, so that means the difference between your lower and upper bound could be huge.
That's right. It could be. Absolutely. And so one of the things we need to do, because we're considering over sort of all possible forwarding states. And, you know, if it's huge, if the difference between the bounds is huge, you could argue that that's a badly designed network. It means the behavior of the network is a very strong function of exactly the details of the routing protocol and the link weights.
And you might argue that that is needed because that is the only thing that's going to allow you to do failover easily, right? You need to be flexible.
No. I mean, I think that this is exactly the set of questions we should be asking. And I think that this reachability analysis gives us some tools to start asking these questions. The answers are not obvious. I think and that remains sort of interesting future work. To say now, if I have this ability to do this analysis for networks, does that help me guide me towards building real new networks? It certainly can find holes like this. It can also lead me to, you know, decide to be more paranoid and put in more filters of various kinds inside my network, right? But it then begs the question, okay, really, what does it mean if you have a network design where the upper and lower bound are very far apart? What it means is you're going to have trouble predicting behavior of that network. Let me just sort of wrapping up this one part. If you do the analysis on the lower bound, you'll basically find that before these extra packet filters are added, the lower bound on reachability from the Chicago front office to New York City front office does in fact include packets coming from the Chicago front office. That's good. Basically, that means that under all possible forwarding states, packets are getting between the two front offices. When you add these new packet filters, it'll point out to you that, oops, effectively you removed those packets that you wanted to be able to get through. What are the takeaway points from this? All right, so we've got this algebra for modeling reachability. The cool things about it, we can model packet filters, routing protocols, and some common uses of what are called network address translators. There's not a lot of related work here. Basically, Tim Griffin and Randy Bush have a paper in Infocom where they validated or came up with necessary and sufficient conditions to validate a particular type of virtual private network called the BGP VPN. It's also RFC 2547 VPN. What's the status of our reachability work? Well, so it works on test cases. We're in the process now of really trying it on some of those production networks. So I can't yet tell you that this is really useful to real network designers. That's something we're still trying to figure out. The strength and the weakness of this approach is that it is a static analysis approach. So you can validate that a network meets certain sets of static objectives. That's really handy. It turns out if I went into all the details of the algebra, there can be false positives. Generally, they're conservative. So if you're validating a security policy, the algebra will tell you that a packet can get through the network, where in reality, under all sort of reasonably foreseeable forwarding states, it won't. You can't use this, though, to actually design a better network by itself, right? You can't say, OK, I want a particular security policy. Use this technique to build me a network that has it, right? This is a tool for analyzing networks and maybe figuring out which networks are good or bad. And you really can't say anything about a whole bunch of dynamic objectives, transient behaviors in routing protocols, right? Traffic engineering. We can say nothing about whether your packet's going to take 40 milliseconds or 100 milliseconds to get through. All we can do are sort of these, is it possible for your packets to get through or not?
So is there any reason why this wouldn't work with higher level entities like firewalls and so on that we're filtering based on?
It might. I mean, so Network address translators we use as one example of a packet transformer. So to the extent that I can model a firewall as a packet transformer, I can probably handle it. Basically, what I have to be able to do is I need an inverse of the set injection. So what a packet transformer does is it takes one set of packets and injects it into a space of another IP packets. And I need to be able to model the inverse function of that transformation, so that basically when I'm doing the calculations to see what sets of packets coming in are going to be allowed out, I can cross that gap. And so for some classes of network address translators, that inverse function is reasonably well defined, but not for all. More questions on this? OK. So we came up with this way of trying to predict network behavior. And I guess I would like to believe that I've convinced you at this point that it's possible to predict some classes of failures that we can't predict today. However, there's a lot that's missing. So let's step back. Let's think about the problem of controlling and managing networks and try a radically different direction. And I'm going to be deliberately inflammatory as I do this. Before I launch into that, though, let me back up to this question of, does control and management of networks actually really matter to real people? I'm going to argue the answer is yes, and I'll start with an example from home. So back in 2001, Microsoft had a little problem in that a lot of its web servers, MSN, support.microsoft.com, basically fell off the net. They were unreachable for various sites for 23 hours. The problem ended up being there was a misconfiguration in routers that controlled access to the DNS servers. And it took 23 hours to find. And if anyone here was actually involved in debugging that, I would love to hear the detailed stories, because all I have is what's been pieced together from various things. But I think that this is a testament, basically, to the fact that it can take a bunch of really smart people and a long time to debug mission-critical applications, because these things are really hairy today. A major ISP tells me that 50% of their outages occur during planned maintenance. So they knew ahead of time that they wanted to make some change to their network. They could have taken any preparation steps that they wanted to. But when they went in and started making the changes, something somewhere else in the network broke. Okay? And this is a very well-run network.
How much time do they spend doing planned maintenance?
Multiple times a week. I mean, it is a continual, ongoing thing throughout their network.
So it's not surprising that most of their outages occur during something that's happening all the time.
Well, no, because the theory is, why do any outages happen during planned maintenance, right? You should be able to arrange the network so that your upgrades.
So when you say during, you mean and also caused by.
And also caused by.
Okay.
Yeah. Oh, yeah. I'm sorry. Yes, this is not. If you unplug the connection to a customer, the customer will experience an outage. However, a customer someplace else should not experience an outage as well.
So more specifically, you mean unplanned outages? There are planned outages during maintenance.
So here's something where I'm going to hedge a little bit, because this is me reporting the words of somebody else. And so I had an extensive discussion with this person, and this is the person who actually runs network operations here, and so has a very good view. But I don't want to make a stronger statement than I can really support. This one is ironclad. These people measure defects in sort of problems with their IP network and the telephone network that these folks also manage. And but anyway, their IP networks currently have 2 to 3 times the defect rate or the outage rate as their circuit switch networks. And this number has actually come down by well over an order of magnitude in the past 5 years.
Seems really good.
But it's but still, IP is supposed to be this very robust thing.
Yeah, that's what we say to the great unwashed.
Right,
So
but
how is outage defined here? Is outage defined as if I randomly inject a packet in the network from a source to a destination?
This does not include transient packet loss. This is factoring out transients. This is, again, so this whole talk is about outages that last for sort of minutes to hours. I'm not talking about an extra 1%. I'm not talking about temporary congestion things. This is busted. Okay.
And are these outages where one machine cannot reach another, and where an existing path, where there is a valid path between them, or is customer only has one link to the network?
No. We factor.
Okay.
All those simple degenerate cases are taken out here. Yeah. No. These are the hard ones, right? These are the hard ones. Well, OK, more questions on sort of motivation. I guess I'm trying to convince you that really there are problems out there. And those problems are performance impacting. And here are some examples, and we could talk about more. But how can we go about fixing it? Well, I'd argue that if you step back and look at the problem of network control, there are 3 principles that would help you design a system to manage networks better. The first one is what I call network level objectives. So there should be possible to directly express the goals of your network. If you want your network to maintain some kind of reachability matrix, you should be able to feed it the reachability matrix. If you want it to do traffic engineering to balance congestion, you should be able to specify traffic engineering rules. Today, all of these network level objectives are buried in the specific settings of configuration parameters in those configuration files that I saw you are assembly language gobbledygook, right? There's sort of, it's down here rather than being directly expressed in any reasonable form. Is there a question?
Are there already tools for kind of doing that?
No. So the holy grail has been, of network management has been sort of policy-driven networking, where you'd effectively take these and you compile them down into configuration files and put them out on the networks. Hasn't worked for a couple of reasons. One, people generally haven't gotten the abstractions right that network designers care about. That's one reason we did this reverse engineering study of real networks to try and understand what were the abstractions you need to support. The other thing is that configuration programs create this big distributed system, and it's really hard to predict the behavior of that big distributed system, right? So even if you configure your high-level objectives down into configuration files, it's very hard to get a set of configuration files that actually make the network do what you want. The next principle I'm going to argue for is what we call network-wide views. Somewhere in your network, you're going to have some logic, and the job of that logic is going to be trying to make the network obey these objectives. Now, that logic is going to be a bunch of algorithms or polygraph algorithms, linear programs, that sort of stuff. But what is it going to need to run on? Well, it's going to need to run on a view of what's happening in the network, the state of the network. Right now, this notion of network-wide view, what's going on in your network, has to be cobbled together from multiple information sources. It's really painful and hard to do. There's no good reason for it. We should make that sort of providing a network-wide view priority number 1 of the network devices and the network architecture itself. The final principle is what I call direct control. So once you've got some management logic that you've fed with desired objectives, and you've fed it the current state of your network, it's going to crank and it's going to come up with the desired state of your network. Why don't you let the management logic directly put the network into desired state? Today, you have to go through this crazy sort of decompilation process of taking the desired state of the network, turning it into configuration files that when you load them onto the routers and run them, will hopefully get the network into that state. Let's just cut to the quick and allow direct control. Now, we sort of took these principles and came up with an architecture that I call a 4D architecture because it has 4 planes and they each start with D. The decision plane lives on top. Now, what we're going to do is we are going to pull all of the management and decision logic that currently exists on the routers or anywhere into this decision plane. And in fact, we're going to centralize it on centralized servers called decision elements. What am I saying? OK, I'm being provocative. We're going to lobotomize the routers. We're going to pull all those routing processes off of them. They don't need to be there. All right? We're going to take all the ability to calculate routes, packet filters, all that stuff, and put it on these centralized servers called decision elements. OK. The decision elements are then going to be able to use network-wide views to compute a desired state that meets the network-level objectives, and then directly control the data plane where the routers live to implement that solution. Hang with me a little bit more. So if the plan here is to basically separate the body, the routers, from the brains, the logic that's going to control them, you need to have a really robust communication path between the brain and the body, right? So that job falls to the dissemination plane. The great thing about this architecture, though, is that the only goal of the dissemination plane is to create this robust communication path between decision elements and routers. There's no notion of sort of policy or trying to implement packet filters or route filters or any of that stuff here. All of that network level logic can exist in the decision plane. Okay. Now, the other thing that we're going to need sort of running on each of the routers in the network is what we call the discovery plane. So each router should be able to discover its own local environment, how much memory it has, how many forwarding tables it can support, who its immediate neighbors are, so that it can report that information through the dissemination plane to the decision plane where it can be assembled into a network-wide view that's going to be used to drive the decision logic. And then finally, you've got a data plane where you have a bunch of routers or switches spatially distributed in space, basically just like we have today. I could go on at length about changes I'd like to make there, but I could even sort of play with today's devices if I had to inside this 4D architecture. Here is a picture summarizing the way networks are managed today. Quickly, there's the data plane where you've got routers distributed in space, and there are a bunch of packet filters on them. The routers all have a forwarding information base or forwarding tables loaded from this control plane where I have a bunch of routing processes running all the routers, which have lots of policies and link metrics and all yada, yada, yada. And it turns out that the behavior of this is so complicated that you need another plane, generally called the management plane, which the network operator has to cobble together out of a bunch of scripts and programs and applications to try and figure out what's going on in the lower planes and fix it, or somehow figure out a way to change it and make it right if it happens to be broken. Now, the way the management plane controls all this stuff today is, as I say, by rewriting the configuration files, trying to dynamically change the programs of the running network, the distributed system, in real time to try and get it to do the right thing. And it has to do this by cobbling together information from a whole bunch of different sources, which are never really designed to be integrated together. Having tried to do this, I can testify to how painful it is. This is one reason why I think the 4D architecture makes the world better. It's just the right set of abstractions to represent the problem of network control and management. Today, we have this management plane. We have a bunch of logic looking at what's going on in the network, trying to rewrite configuration files that get fed into the control plane. So when the control plane, that distributed system, operates in real time, will produce the right forwarding tables and packet filters and stick them in the data plane. In the new world we're proposing, basically, we've gotten rid of all the redundant logic that exists in the management plane and the control plane. Today, you have the management plane trying to predict what the control plane is going to do. We're saying collapse that down, just have the decision logic directly compute the forwarding tables and the packet filters that the data plane needs. Right? And then it's going to be delivered from the decision elements to the data plane via the dissemination plane. Okay? So by eliminating this duplicate logic, we make life much easier. And I also argue we get a lot more robustness. 3 key questions that I often get asked about this point in time. The first is, OK, could you actually ever deploy this? I mean, is this purely sort of a theoretical investigation? Second, is this feasible? I mean, if you actually built a network with a 4D architecture, would it just fall on its face? Could it actually work? And then third, OK, so the 4D architecture maybe can run networks the way we do today, but that's no reason to actually investigate it. It has to be able to do things we can't do today. I'll take those in order. But yes, Venkat.
It seems like there are multiple groups that are proposing basically this idea of separating routing computers. Can you sort of say, oh, OK, good.
So I claim it's deployable because there are a bunch of industry trends, including in the Internet Engineering Task Force, the Forces Working Group, GSMP, GMPLS working groups. At Lucent, there's a group working on what's called soft router. And they're all basically trying to find ways to separate the hardware forwarding platform from the software that runs on it. I think that's great. That's exactly the platform that I would want to implement my 4D architecture on top of. The thing that I think I'm adding to that is this notion of how to structure that software. Right? The way you fix this problem is not by separating software from hardware and then taking OSPF and BGP processes and running them on a really fast server so they just run faster than they do today. That just causes more problems faster. Right?
But do you know why, Dave? This is, you probably already know, one of the problems here is that any of the vendor advantages out this way, right? You standardize the thing, you commoditize the hardware, and then apparently nobody can sell for expense, right? And this is, in fact, this has happened many, many times in different domains.
Yes.
In fact, it's happened recently with other stuff that we can talk about later.
I mean, I sort of joke. I mean, the reason Cisco and Juniper exist and have the market advantage they do is because they have the only 2 interworking BGP implementations. And that's because they were written by the same guy, Tony Lee, who was at Cisco, and then he went to Juniper. And then he went to Procket, tried to write a BGP implementation for them, but that company didn't work out for other reasons. Yes. However, I mean, that's why Lucent wants into this business. Lucent knows how to build hardware. They have no clout for writing software. Right? So that's why there are really people out there who are probably going to build these things. There are 3Com and Extreme who build Ethernet switches. Ethernet is getting more and more complicated. Basically, it has sort of the same kind of features that you want in IP being re-implemented in Ethernet. They haven't even figured out any way of controlling that stuff yet. We can control those Ethernet switches with a 4D architecture. I mean, why are 3Com and Extreme doing it that way? Well, because no one has control over the Ethernet space.
So it seems to me that one advantage of having the routers essentially being their own little autonomous thing is that if what you're calling the dissemination plane were to break, the router is still doing something reasonable.
Let me get to that in the feasibility. So I have that as sort of my feasibility thing. Let me get to that in a moment.
Okay.
I just want to say that your characterization of soft router was not quite correct. It's not like they take a bunch of OSPF processes and run them on the central server. If you take a bunch of OSPF processes for routers that were in the same domain in some area, same AS, then you can run one OSPF process, right?
That's right.
So it's not that they run multiple OSPF processes on the same machine and make it
That's right.
faster.
Effectively,
they actually reduce complexity.
Well, no. What they're basically, if you go back to my routing instance graph. They're running one routing process for each of those instances, right? But still, notice I took that big network. It was still a pretty complicated graph, adjacency graph. There's still all sorts of packet filters and policy and stuff being applied. You haven't addressed that problem. I mean, basically, a routing instance is a pretty simple thing. That's why I can abstract it. So I claim that there's lots of savings left that we need to get, lots of advantages that haven't been tapped simply by having this platform available. Okay. There is an incremental deployment path. Basically, an individual network can upgrade to 4D. You don't need all the networks everywhere in the internet to upgrade to 4D at once. You can use BGP or any kind of way of getting hierarchical relationships between networks that you do today. I can talk more about this. Arguably, small enterprises are actually the ones that have the most to gain. Why? Because generally the people who run the networks for small enterprises are people who normally do Windows help desk. They are not network engineers. They had a Cisco CCIE sales guy come and help them design their network once, and they were then tossed their own. Anything we could do to help them out would be tremendously useful. Also, I should also point out that you don't need to make any changes whatsoever to the clients at the edge, right? I mean, we're still carrying IP packets, right? So the hosts and the servers require no changes. Now, they could do very interesting things talking to decision elements, like a bunch of servers could talk to the decision element and say, hey, I happen to know the access list for who's allowed to access which file servers and things like that. I'm just going to set the network up to enforce that now, getting another layer of security into the system. OK, but let's go to these feasibility questions. Now, I consider myself a systems scientist. In my mind, that means that I like to look at sort of a big problem, sort of formalize a problem space. What is the research problem here? And then come up with hypotheses or principles or architecture to solve it. But then you've got to validate those. And so I believe in doing that by building prototypes and then measuring them. So that's what we did. We built a prototype of the 4D architecture. It was deliberately quite simple. Our decision plane, basically our decision elements have logic to simultaneously reason about reachability matrices and computing routes. I picked these two because people haven't looked at these before. I could easily toss traffic engineering in. But these two cover a space that I argue is quite interesting. We actually do connect multiple decision elements per network. We use a simple election protocol. So if the network were to be partitioned up, basically the dissemination, if there's a decision element in the connected component, then that decision element will take control of that connected component. If there is no decision element in that connected component, then those routers are sort of out of luck. And I'll leave it there. Our dissemination plane, so this is the thing that's supposed to provide very robust communication between the brains and the body. I use source routes to directly control messages. I like source routes. If you know my history, you can probably guess why. In a nutshell, basically, source routes are extremely simple. Each of the individual routers and switches need to know nothing of the overall topology. They just need to forward packets according to the source route they were given. It turns out that you have complete flexibility to take advantage of any connectivity in the physical graph, whether that happens to be sort of actual links that user data might flow over, or a separate supervisory network, or even dial-up modems that only go into effect when other links have failed. Right? You can very quickly load balance your control and management traffic across all that physical connectivity.
So when a new forwarding element is added to the network, does it have fully configured routes to talk to whatever it's...
So that's also the great thing, right? So we effectively get zero device-specific configuration. When you plug in a new device, it needs basically a security certificate to know which dissemination plane it should be part of and which decision elements to follow commands from. But that's it. In our architecture, our prototype rather, we use beacons that come from the decision elements to create reverse routes through the network of these source routes. That's what I mean. It's very simple and easy to create robust routing here. But again, the notion of the dissemination plane architecture and the 4D architecture is you just need robust communication. There's a huge amount of really good distributed computing and sort of systems research that could be done on getting the best possible dissemination plane. I'm going to argue that this one we have is good enough for the examples I'm about to show you. I'm not saying this is the end-all, be-all.
I'm not convinced that this is going to be very robust. For example, if you have, let's say, you lose reachability in the dissemination plane because the link got flooded because of an attack.
Yes.
You would like the routing element to autonomously decide that, okay, I should start filtering traffic or do whatever.
No. That's the beauty. I mean, you're presupposing lots and lots of smarts in the routers that doesn't need to be there. I mean, we could put that kind of smart.
How are you going to solve that problem in this context?
So what we do is we're going to use some periodic beacons. Decision elements are going to ask the routers, send me your state. If they haven't heard from a router in a while, they can actively ping it. The decision elements actually know, the decision elements have this network-wide view. So by putting together the discovery information from each of the routers, they have the overall network topology. They know they can route around congestion.
But you've lost connectivity to that router because the router is flooding traffic on all its links. I mean, it doesn't know any better. I mean, it's just getting traffic and it's sending it out on all links. Everything is fully utilized. The central decision.
If that's really the case, simple prioritization would help, right?
This is one example. I mean, it just seems like...
Well, no. I mean, like I say, I'm being provocative, but I'm claiming that for most of the shotgun blasts you can level at this, there's some pretty easy fixes. I mean, it's not crazy. Let me just sort of show you why this is not completely crazy. All right. So we evaluate it using Emulab. Why? Because as an academic environment, I don't have racks full of computers, but I do have access to Emulab. We use Linux PCs as routers. And these were, state-of-the-art as of like '98. These are not the world's fastest machines. We tested on 9 enterprise topologies, going from about 10 to 100 routers each. We did sort of a bunch of the experiments you would expect. How long does it take when you cut a single link failure? Well, we recover in less than 300 milliseconds. Right? And what that is most of that time is the 100 or so milliseconds it takes us to actually detect that the link was down. Why? Because we're using hello packets as heartbeats over links, because these Ethernet links don't have any kind of hardware detection. One of the things I would love to put in the data plane is some kind of hardware support for link detection. Generally, again, I'm not trying to say the 40 is the best way to do it, but I'm going to say here that we're comparable. Today, a response in less than 1 second is considered excellent. Basically, you have to do a lot of work to tune your network to get sub-second reconvergence under single link failures today. And we've got that. We say, OK, what happens if you take the decision element and you shoot it? Well, OK, we have a very simple election protocol, which takes about 1 second to nominate and elect the new decision element. Right? Now, I should argue that just shooting the master decision element doesn't change the user-perceived behavior of the network. Right? When you kill the brain in this case, the body continues to live. There's no disruption unless a second fault occurs, because that's the only thing you need the brain for, compute new routes. And maybe a 1 second vulnerability is sort of good enough. Maybe we need to push this down to a smaller window of vulnerability. Those are all questions that we can tackle and refine. Then we asked, OK, well, what happens if we take out the sword and just start hacking links out of the network, hacking links and switches out to just completely partition into multiple pieces? And effectively, with less than 1.5 seconds of outage, we have completely restored all the connectivity that was left in the network. I mean, clearly, if you have disconnected components, you're not going to get packets between things in those two components. But maximum connectivity is restored. And these are the kinds of failures that they really just don't happen very much in real networks. Like when you look at the kinds of failure situations, these total partitions are incredibly rare. A nice thing about the 40 architecture is that, as I'll say on the next slide, we've sort of separated distributed systems issues from networking issues. Right? You can now control the reliability of your network by how many decision elements you add to it and where you put them. If you have a bunch of routers, you're like, geez, if these routers get cut off from the rest of the network, I really want them to continue doing useful work. Put a decision element in there with them. If you have a couple of routers and you're like, geez, if these routers get cut off from the network, no useful work can happen because those hosts are mostly just talking to file servers that now they have no link to. So those routers don't need a decision element in them. And you see, you can think about these issues separately. And I argue that that's a great savings and simplifies the design problem. Rich and John.
Is there any reason not to put a decision element in every router?
You could. That's trading overhead. Basically, so if I went into the details of how we're doing this, more decision elements is sort of more overhead. At some point, maybe it's too much overhead. Maybe there are ways of reducing that overhead further.
So in a sense, isn't this just consolidating routers? You could treat this as putting a whole bunch of routers into one box with just one decision element?
No, I argue it's not, because the routers are fundamentally distributed in space physically. I mean, they really are out there in space. They really have non-zero propagation delay among them.
But logically, you can look at it that way still?
Yeah, that's it. So logically, from the point of view of the management logic gets that nice, simple textbook view of, I have a graph. The graph has properties. Let me compute things on this graph. And that's sort of why it's simpler to do the network logic now.
So how far do you take this? Would you have one decision element for the entire internet?
So I don't think you could do that for a couple of reasons. One, there's a scalability issue. Distributed computing techniques can only get us so far. Two, trust boundaries. These networks all exist to serve some mission. And the people who create that network, may not trust their neighbors. In fact, they almost certainly don't. They probably don't even want to tell their neighbors what their policy is. And so, there will always be separate networks.
So you're saying this replaces OSPF but not BGP?
That's right. So there's still a question of how should different networks talk to each other. Today, BGP is the protocol used for it. BGP has lots of problems. I'd argue that one, I haven't looked at the hierarchy. I call this the hierarchy issue. Basically, how do I compose 4D networks together into a larger internet? I haven't looked at that one because all the work that's being done on BGP improvements is applicable here. So I don't want to duplicate the work of other researchers. The other issue is that I think that if we can simplify the behavior of each individual network, it becomes much easier to simplify sort of the behavior of the composition of those networks. For example, something called the hot potato routing problem is a big problem for transit providers today. Basically, I have two egress points, and which egress point I use for my traffic depends upon which of these egress points is closest to me. During maintenance, or during a temporary event, I needed to take down a link such that what was the closest egress point becomes further away. In a real network, this can basically turn into tremendous traffic sloshes. Huge amounts of traffic that used to go this way is now going this way to a neighbor who wasn't prepared for it, didn't know that it was coming from, couldn't predict it, right? Unless I gave them my maintenance schedule, which I'm not going to do because I compete with those people. But really, why is that? What I'd like to be able to do is structure the decision logic inside my network so it says, during temporary planned maintenance events, don't change the egress point computation unless there's a really good reason to it, meaning complete partitions or something like that, right? So we could simplify the behavior of individual networks, and that'll simplify the behavior of the internet as a whole.
But you think it'll sort of scale, this will scale to the size of the ASs out there?
This will scale to the ASs out there. I mean, our back-of-the-envelope calculations show this working up to 10,000 routers without a huge amount of problem, and more than 1998 state-of-the-art machines. But okay, let me go back and sort of show you that I think that the 4D architecture can do. Yep.
5 minutes.
5 minutes. All right. So remember this problem where packets got through because there's a security violation? What we do, we set up OSPF, sort of at the typical routing design today. We happen to use the Quagga implementation. And we look at the packet loss rate for packets going from Chicago front office to New York City data center. It starts out at 100%. Why? Because this is a packet flow that's supposed to be prohibited. The green arrow is when that new shortcut link between the two data centers comes up. What you see is about 600 milliseconds after that link comes up, OSPF has recognized the new link, has reconverged, and packets are now going around the packet filter, which should be a prohibited flow is getting through. In the 4D architecture, we start off at 100% packet loss as desired. The new link comes up about 200 milliseconds later. The decision element is react. It rewrites both the packet filters and the routes, and it does so in a consistent way to ensure that the reachability matrix is upheld, no packets leak. There is also this issue where there's a physically connected path between the two front offices, even when that link between them fails, but it can't be used in the conventional architecture because of the extra packet filter. When we set it up in the conventional network, experimentally, that's what we see. Packet loss rate between the two front offices starts off at 0. When the link fails, packet loss rate goes up to 100%. It turns out that routing has reconverged. It's just that it's reconverged and sent those packets into a black hole. They never get through. In the 4D architecture, the link fails. We do, in fact, see a temporary outage. But within 300 milliseconds, everything's back to normal. Right? About 200 milliseconds out, the DE rewrote all the packet filters and the routes. So, I mean, there is some related work here. Basically, there's been a move towards driving network operation from network-wide views, traffic engineering, traffic matrix computation. All that stuff is applicable in our space. Let me just finish this quickly. There's also been a move towards centralizing decision-making, routing control point, Nick Feimster and Jennifer Rexford, path computation element. They have primarily looked at the interdomain side. In fact, I've been doing a lot of work with Jennifer Rexford. We're sort of working on the intra-domain problem. She's working on the interdomain problem. We actually plan to combine the two in the future. Signaling System 7, the phone system, used centralized decision-making. But I'd argue that, again, there's some pretty significant differences between our architectures. Yes?
So you showed like delays 200 milliseconds before your decision element was responded. Was that simply propagation delay, or was it something else?
It's about 100 milliseconds to even detect that the link has changed. Then there's time, propagation delay to get the information in the decision element, compute the new routes, load them back down in. I can show you breakdowns of all that if you'd like.
You said that the 4D architecture was foolproof, right? But you could make the same kind of mistakes while specifying reachability there.
Yes, you could give the network the wrong objectives. Absolutely. I mean, that's sort of
that was the only mistake that was made in the previous example, right?
No. The mistake wasn't in specifying the reachability matrix. It was translating it into the packet filters. It was going from the desired objective to the grotty mechanisms to implement that today. Takeaways from here. I'm arguing that we should think about getting rid of the complicated distributed system in the control plane. The 4D architecture is a promising approach. Basically, you get coordinated state updates. And this key issue is you get to now think about the network logic, how you want to do egress point selection, traffic engineering, all that stuff, separately but coherently. And separately, you get to think about distributed systems issues. How do I want to get robust communication between decision elements and routers? How do I want to achieve scalability? Those things. And so that's great. Now you can you don't have those conflated the way we do in today's architecture. And so finally, networks have to meet different objectives. Today, we use control planes. It's hard to predict what they're going to do. And if you refactor into a 4D, it seems promising. Anyway, more questions, or are we out of time?
Yeah, I think we are out of time because we want to talk to you separately too.
Okay.
You guys
Thank you for the very lively discussion during the